It's May 8th, 7:31 p.m. I will call the meeting to order. I am Jay Lavender, president of the RASC Edmonton Center, and I will be your host tonight for tonight's festivities. I will ask up front, we have many folks that are recording the game at home, so please no blurting out scores or boos, hisses, or cheers, if at all possible to oppress that. Thank you. Okay, let's get rolling. So first, a couple of housekeeping items. So our April 17th meeting minutes have been posted to the OneDrive. I'm sure everyone has perused those minutes, and I'm wondering if anyone has any errors and omissions for our last meeting minutes. Okay, hearing none, over to you, Madam Secretary.
I move that the meeting minutes be accepted as posted to the OneDrive.
Thank you. And do we have a seconder? Denny, thank you. And can we get a vote from all the members? All in favor? Any opposed? All right, motion carried. Thank you. Okay, so moving right along here, we have a guest speaker, and I am going to ask Dr. Morsink to please introduce our guest speaker.
Thank you so much. I always say it gives me great pleasure to introduce our next speaker, but this time it's more than a great pleasure. Stephen Portillo actually first got interested in astronomy because when he was a kid, he used to come to the RASC Observatory located just outside of Telus World of Science. And I just find that really inspiring that he now has a PhD in astrophysics and is now an assistant professor. So, and maybe he can tell us a little bit more too about what it was like to visit the RASC Observatory back in the day. In fact, I recall some time ago, I guess it was more than 10 years ago, I think it was Cornelia Blanc who was telling me, you know, we have this one really brilliant kid who keeps visiting, and you know, he's going to come to the University of Alberta. You should watch out for him. And then one day, when I was just talking to people, I was just thinking, wait a second, I bet you this is who Cornelia was telling me about. Okay, so anyways, so Stephen graduated with his BSc in astrophysics in 2012. And then he went to Harvard University to do his PhD in astrostatistics. And then he was a Dirac postdoc at University of Washington in Seattle. And then a year ago, basically, he came back to Edmonton, and he's now an assistant professor at Concordia University of Edmonton. And so I'm really happy that he's here. And could you come, please come up here.
Thank you for that introduction, Sharon. And like Sharon said, it's great to be back in Edmonton where I first got into astronomy and, you know, to be giving a talk at this venue. I'll also give a shout out to Dr. Morsink. One of my first interactions with her, I think, was when she was helping me write an application for NSERC funding for my PhD. So before I go ahead and tell you more about the research that I did in my graduate studies and postdoctoral studies, I have something completely different first. We'll actually have two musical presentations tonight. Let me get the screen share on. So what I'll start off with is actually a music video that a bunch of classmates and I put together during PhD studies. So for context, this is part of one of my classmates, Andrew Vanderberg, now a professor at MIT. He decided to do a dance your thesis. Okay. So yes, he decided to do a dance your thesis. And the context for his thesis starts in 2013 when the second reaction wheel on Kepler broke, which made the original Kepler spacecraft mission to look for exoplanets impossible. But NASA and Ball engineers actually came up with a clever solution to salvage the rest of the Kepler mission, and they called it K2. And it took advantage of actually using the radiation pressure from the sun to stabilize the aircraft instead of the reaction wheels. My classmate, Andrew Vandenberg, worked on ways to analyze this data. The engineers couldn't get the data to be quite perfect again, and his work was about, how do we use this new spacecraft to still look for exoplanets? The following video is a musical interpretation of the NASA and Ball Aerospace engineers. So without further ado, I present you Go K2.
This telescope could be stabilized, solar pressure utilized, full potential realized. Well, it could be K2. We'll use the solar radiation, catch those photons, oh yeah.
Keep talking, whoa, keep talking.
Balance out the pressure, keep it nice and stable, oh yeah.
We'll get the funding, yeah, we'll get the funding.
With new targets every run, we'll be having lots of fun. You know that it's legit, we'll be seeing that transit with K2. Go K2, we'll get you up and running now.
Go K2, go K2.
Go K2, you're finding super Earths, oh wow.
Go K2, go K2.
You are for real, no reaction wheel. You're K2.
That's Professor Vandenberg in the Kepler spacecraft costume, by the way.
Go K2, go K2.
You are for real, no reaction wheel. You're K2.
So just in case you were worried I wasn't having enough fun in grad school, there you go. Oh, with audio, excellent. All right, so now I'll tell you more about the research that I started in grad school, all about astrostatistics. And my subtitle here is alluding to the fact that when I started my PhD, I had no idea that I would go into astrostatistics and computer algorithms. That wasn't really on my radar. And so grad school is maybe the process of how I learned to stop worrying and love computer algorithms. But with my first title here, Computer Enhance, what I'm hoping to evoke are those scenes from like crime TV shows and movies where the main character calls upon their technician to use some magic computer algorithm to take some blurry image and find the suspect. So just as an example of some of those scenes where a main character says computer enhance. There we go.
Got an image enhancer that can bitmap?
Maybe we can use the produce send method to see into the windows.
This software is state of the art.
The eigenvalue is off.
With the right combination of algorithms.
He's taken illumination algorithms to the next level, and I can use them to enhance this photograph.
Lock on and enlarge the z-axis.
Enhance.
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 Freeze and enhance.
So clearly in a lot of these TV shows and movies, computer algorithms are just convenient technobabble to advance the plot. But these sorts of algorithms are not completely in the realm of fiction anymore. One example that maybe even some members of the audience might be aware of are AI-based algorithms that can remove noise from astronomical images. And so, this talk is not sponsored, but as a good example of such an algorithm, I thought I'd share a clip of this YouTube astronomer reacting to this AI algorithm called Noise Exterminator and how well it seems to clean up noise in astronomical images.
So let's zoom in, for example, around the Rand Nebula. And as you can see, the noise is everywhere here. So there's plenty of noise. And now I'm going to apply the plugin. Ooh, that's a huge difference. That's a huge difference. And so what I learned about this AI is that it's smart enough to not affect stars and objects. So let's see if that's true actually.
So, it's not quite, saying zoom and enhance and you get a picture of a suspect from the reflection off of a metal mug or something. But we do have computer algorithms that can do really impressive things with images nowadays. So if we think back to those crime TV shows, one way to think about what the algorithms are doing is they're answering this question. How can we make full use of the images that we have to catch the perpetrator, catch the suspect? And maybe, the investigators are in a tough spot. They've got really limited evidence. The only thing they have are blurry photos or mirror reflections, but they still want to do everything they can to catch their perp. The computer algorithms that I'll tell you about tonight, I think, are actually answering a very similar question. So just like the investigators on those TV shows, we have a limited set of evidence about the universe. We're kind of stuck here on Earth. We need to build telescopes in order to observe the universe. We have a limited set of images, and we want to make full use of those images to make as many astronomical discoveries as we can. And so this is really one of the motivating questions behind the sorts of algorithms that I like developing. And to place this sort of work into more context, I'll give you kind of how I see the different roles or specializations in academic astronomy. And I'll start off with, the sort of thing that I might have learned from Professor Morsink back in my undergrad days about how the scientific method works, where in astronomy, you've got one set of scientists that we call the theorists, like Stephen Hawking and Colin Williams here. And their specialization is to think about the physical theory and come up with ideas of things that might actually be observable in the universe. And they focus on the math and the theory. And their end goal is to make predictions about what we should see in the natural world. And kind of to complete the scientific method, you have people that focus on theory, but you also need people that focus on observation, like Vera Rubin here. So for the most part, astronomy is not an experimental science. I don't remember the last time I poured chemicals on the sun. So as an observational science, we need people that focus on making observations and thinking about, what are the best objects to observe to test the predictions that the theorists are coming up with. And so you've got these two arms of science, theory and observation, that complete the scientific method. And so our observers are really trying to make measurements in order to test the predictions that the theorists make. And they tell you in undergrad, this is how science works. This is the scientific method in action. But as you go further along in how astronomy works, if you think about the telescopes that we have nowadays to do research astronomy, they're really just marvels of engineering nowadays. The optics, just even the mechanical structures that are involved, the complex cameras that we have, it's become clear in astronomy that we have, kind of a third group of scientists that have focused on what we call instrumentation. They think about the hardware that we need in order to make the observations that we need to test the predictions. And so these are the people that are thinking about, how do we make the best cameras and spectrographs and telescopes? And these instruments have gotten so complex that we need people that specialize in that sort of thing to think about the instruments that we need in order to make the measurements that we need. Now, the next idea that I'll present to you is something that I first heard from Professor Mario Jurich over at the University of Washington, Seattle. And he argues that just like you have people that specialize in hardware instrumentation, cameras, electronics, optics, astronomy is also starting to develop into a state where there are people that are focusing on software instrumentation. And so it's software, pieces of code, computer algorithms, but it's also a type of instrumentation in the sense that it enables the sorts of measurements that astronomers want to do. It turns out that the data that we're collecting are so complex, and we're also collecting more of it, that it becomes useful to think about the different computer algorithms that we can use to best analyze that data, to make the most use of it. And so we can think of these algorithms as kind of a piece of software instrumentation that we have to use after we collect our images from our telescopes and cameras. And tonight, I'll give you two examples of software instrumentation that I've worked on, and hopefully convince you that, computer algorithms are becoming a part of how research astronomy is practiced nowadays. So the first of the two examples that I'll show you is work that I started during my PhD thesis. And it has to do with crowded images, like this image of Messier 2 from the Sloan Digital Sky Survey. And so Sloan Digital Sky Survey, taken with a ground-based telescope. And you can see that if you try to look at the very center of this cluster, it's very crowded. The stars look like they overlap with each other because the atmosphere is blurring the images that we get. And so, you might think it's impossible to even tell what's going on at the center of this cluster. But what I'll present next is how we can actually still use images like this, even if they are really crowded. And so this is work I started in my PhD thesis with my supervisor, Professor Douglas Finkbeiner, and I did this in collaboration with my grad school classmate, Tansu Dailan, and two students who were undergrads at the time. Now they've advanced in their careers, Ben Lee and Richard Feder. So to start this section off, I'll tell you about what makes a crowded image like this really annoying to use in research astronomy. And so I'll zoom in on a 10 by 10 pixel patch of this image, and I'll pull out just the R band, the red band part of this image. For this section, I'm using the convention that pixels with more ink that are darker up here have had more photons hit them. So these are actually, the dark spots you're looking at are actually like bright spots where stars are. And so kind of the first thing you want to do with an image like this is to figure out how many stars are there, where they are, and how bright each of them is. And kind of the typical step-by-step procedure that you would follow to get a computer to do this is to say, okay, I'm not really sure what's going on yet. It's kind of a mess, but I'm pretty sure there's at least one star. And if I try to figure out where the brightest star in this patch is, it's probably somewhere around here. And then I can go to my statistics textbook, look up maximum likelihood optimization as a way to say, okay, if this star is here, what position and brightness would best explain the image that I'm seeing, what position and brightness best fits all of the pixels that I'm seeing on screen. And maybe it turns out to be where this yellow star is right now. But I'm also pretty sure there's more than one star in this patch of the image. So let's go after the second brightest star. And maybe it's here. The problem is, if we're going to use this maximum likelihood statistic to tell us what positions and brightnesses best explain this image, because these two stars are so close together, they're not independent. The light that is being emitted by both stars overlaps in the image. And because of that, the moment that you include the second star in your best fit, you slightly change, or maybe even dramatically change, the best fit position of the first brightest star. The best fit for the first star independently is going to be different than the best fit of these two stars together. And so neighboring stars that are close enough that their light overlaps in the image affect each other's best fit. And this might be okay to deal with, maybe we just start counting up, right? Here are the brightest two stars. We can repeat this procedure, add a third star in. That moves around our first two stars a bit. Maybe that's fine. The really annoying thing that happens is in such a crowded image where the stars overlap, you might not be sure how many stars there even are, how many you should even include in your fit. And so in this example, maybe we're sure that there's at least these three stars, but we're less sure about these fourth and fifth stars that are less bright. And, you might say, these less bright stars, I'm not really interested in them. They're less bright. I'm not going to get great measurements from them. I don't really care about them. The issue is, even if you don't care about these new stars, including them in your fit will affect the fit that you get for the brighter three. And this is an issue if you do care about those bright three. Even if that's all I wanted from this image, I have to care about the fainter stars, because whether or not they exist, that's something I'm uncertain of. Whether or not they exist actually affects the best measurement that I should get of the brighter three. And this is a really weird statistical uncertainty to deal with. And this process of deciding how many stars you think there are is called deblending. The stars are kind of all blended together and you're deciding how to separate them out. And the issue is, depending on how many stars you think there are, your measurements change. Now, granted, looking at the core of a globular cluster is kind of looking at the most extremely crowded part of the sky. This is, the sort of place on the sky where this pops up all the time. Surely this doesn't happen everywhere on the sky. But the thing is, the better we make our telescopes, the worse this problem actually gets. And so here's a picture of the Rubin Observatory, named after Vera Rubin, under construction on Cerro Pachón in Chile. It's almost done. Like each time I give this talk, I have to update this photo. And so we're building these bigger, more sensitive telescopes, which is great. But they actually make this problem worse, because with a more sensitive telescope, you see more stars and galaxies in the same area of sky. And so the sky becomes more crowded because your telescope is better. But because the sky is more crowded, you run into these sorts of issues much more often. And so we're in this kind of catch-22 where, yeah, we want better telescopes, but now we have to deal with these statistical problems more often. So one solution that I worked on is called probabilistic cataloging, where cataloging is this process of taking an image, identifying what stars you think are there, and then measuring them. And the idea behind probabilistic cataloging is that you don't need to make just one catalog from an image. Instead, the idea is that you actually make an ensemble of catalogs, many catalogs. And the idea is, if you're uncertain about the number of stars that are in your image, you can capture that uncertainty. And in some members of your catalog, you have some catalogs with 3 stars, some with 4 stars, maybe even some with 5 stars, if you think that's a possibility. And the fact that your measurements depend on how many stars there are, you can actually capture that fact because each of these catalogs has, the best measurements attached to it. And, what an astronomer is really after when they make a measurement, like, yes, you want the number that you measure, but as a scientist, you always, always, always want the uncertainty. Like a number is meaningless without error bars. And this is a way to capture our uncertainty about how many stars there even are, let alone how bright they are. And it turns out that the mathematicians and statisticians figured out a framework to do this sort of thing like decades ago. And you can actually make this completely rigorous using a branch of statistics called Bayesian statistics. But I'm not going to dive into the Bayesian statistics. Instead, I'm going to show you this sort of algorithm in action. And so I've been showing you pictures from the Sloan Digital Sky Survey, this 2.5 meter in New Mexico. And what I'll do is I'll show you what's possible with this ground-based telescope, that has to deal with Earth's atmosphere. But to show you how well the algorithm is doing, I'm going to compare with images taken by the Hubble Space Telescope. It doesn't have to deal with the atmosphere. It's going to have a much clearer view of what's going on. And so it'll allow us to check our answers. So here's that 10 by 10 pixel patch again. And again, this is the only image that we're going to give our computer algorithm. If we, flip to the back of the textbook to see what Hubble says the answer is, yeah, that's really complicated. There's way more than 3 stars up there. And given how many stars there are in the Hubble image, you might justifiably be wondering, is it even worth using this 10 by 10 pixel patch? Does it have any scientific value? And most of the time, if you want to do work in a globular cluster, you write a proposal for Hubble Space Telescope time, because then you get these really clear images. But there's only one Hubble, and you have to compete with everyone else who wants Hubble time. There's way more telescopes on the ground. And so if you can get away with using a ground-based telescope, why not? So let's see what the best is that we can do with this 10 by 10 pixel image. So to start off with, I'll show you the results of using kind of a very traditional standard software pipeline on this 10 by 10 pixel image, DAO vote for those of you who are in the know. And so you see 3 blue crosses up on the screen representing the 3 stars that it thinks are there, labeled with their R band magnitudes, 20 point something magnitude for all 3. And it's claiming a 0.1 magnitude error for the brightness of each one. But if you remember that Hubble image, like this is just way off. If we overlay the Hubble catalog with the brightest stars in bright green here, we can see that this traditional software pipeline is giving us a lot of problems. It's not just missing the faintest stars. What it's actually doing is it's blending real stars together. So this blue cross in the lower left is actually a blend of these 2 green crosses that are there. And this is a huge problem if we care about, the population of stars in this cluster, their distribution in how bright they are. Because in reality, there's 2, maybe medium brightness stars there. But our traditional catalog says, no, there's a single bright star. And that's like a completely different answer. Worse yet, these 2 blue crosses at the top appear to be a complex blend of these 4 or 5 bright stars that are closer to the top. And so again, the real answer that's out there in nature is that there are these 5 stars up there, But our traditional software is saying there's 2 stars up there that are brighter than they should be. And so this is the reason that, most of the time, yeah, you want to take the Hubble Space Telescope image. It's way better. But let's see what we can do with just this 10 by 10 pixel image and a little bit of computer algorithm magic. So the probabilistic catalog has shown up in the red X's here. And you can see that it's way closer to the Hubble answer. It's identified all of the bright stars that are there. And so it's going to give us a much more accurate view of what's going on in this cluster. The numbers that have appeared beside each cross are the measured R-band magnitudes of each star. And remember that the main point of probabilistic cataloging is that it doesn't just give you one catalog for an image, it gives you an ensemble. And I can show you that ensemble as different frames of this animation. So each frame is a different possible catalog that fits this image. And so the main thing you'll notice is that the red X's hop around, especially the fainter ones. And that's actually telling us about our uncertainty in the positions of each of those stars. The magnitude numbers are also changing. That tells us about our uncertainty in brightness. But also, this probabilistic catalog tells us about our uncertainty about how many stars are even there. You'll notice that in the lower right, there's a red X that keeps popping in and out of existence. The program is uncertain about whether there's a 22nd magnitude star there or not. And it turns out that's actually a good thing. There is no 22nd magnitude star there. But the fact that there might be is a factor that should be taken account for, that should influence our uncertainty about our measurements of the neighboring stars. And so the program is doing its job here. And this animation looks, really encouraging, but we can take a look more quantitatively at how the probabilistic catalog is performing relative to the traditional one. So this graph is looking at the completeness of both catalogs, or it's looking at what fraction of stars do both programs find as a function of those stars' brightness or magnitude. So on the x-axis, the horizontal axis, bright stars are on the left, faint stars are on the right. And the vertical axis is completeness, which goes from 0 to 1. And so, of course, both programs find the brightest stars. That's not a surprise. But around 18th, 19th magnitude, the DAO catalog in blue, its completeness starts falling off towards 0, and then it doesn't find any stars anymore. The probabilistic catalog, it's not a magic program out of a TV show, so it has to run out of gas eventually. But the probabilistic catalog falls off at much fainter magnitudes. And in fact, this cutoff magnitude is over a magnitude fainter, which means that the probabilistic catalog is able to deblend and find stars that are over 2.5 times fainter using the exact same image. And so, you can think of this as like, I just increased my telescope's effective area by 2.5 using a computer. This is awesome. And so, we're seeing more stars, and we're also getting a more accurate picture of what's going on in this cluster. And so this is an example of using this ground-based data that is difficult to use because the stars are blurred out and overlapping. But with enough statistics and computer power, you can actually still measure a lot from images like this. And so this is the first example that I wanted to go through. The second one is some research that I started as a postdoc over at the University of Washington, Seattle. And it has to do with finding faint asteroids. And specifically, we were looking at faint Kuiper belt objects. And those are interesting because they're, relics from the formation of the solar system. And looking at them and looking at their properties, you can try to figure out what was going on earlier in the solar system's history. And so this is work that I've done with a whole bunch of people over at University of Washington, Seattle. It's a project that started before I got there. And I'll tell you a bit about the sort of work that we were able to do. And to start off with, how do you find an asteroid in an astronomical survey? So I'll show you this animation that's actually a set of images taken by the New Horizons spacecraft of the object Quaoar. And so the idea is that a solar system object, like an asteroid, will move relative to the stars. It's not moving at the sidereal rate. And so if you have a sequence of images taken at different times, you can play Spot the Asteroid. It also has a helpful red circle around it in this case. But you can find solar system objects like asteroids by looking for things that are moving relative to the fixed stars. And for bright asteroids, this is easy, right? They just pop up. But how can we find fainter asteroids? And also, how can we find them without having to make a flip book of all of our images to look for moving objects? Or in other words, how can we get a computer to help us find these objects? So I'll step through the basics of a strategy called shift and stack. So here I've got those 3 frames from that animation laid out, and let's say they're from 3 different nights that we observed the same patch of sky. Now we know that this asteroid is moving really quickly to the right with a little bit of an upward component. So the shift in shift and stack tells us we can shift our images to counteract the asteroid's movements, to make the asteroid stand still. And so if we take our night 2 image and shift it way over to the left and a little bit down, and we do the same thing with the 3rd night's image, we move it even more to the left and more down, we can shift our images so that the asteroid stays in the same place. And if we overlay our images on each other with the asteroid in the same place, the fixed stars will just kind of blur out in the background. And we can take these images that are shifted and stack them, add them together, just add the brightness in each pixel. And when we do that, we can get a really nice image of our asteroid because we're actually combining the brightness that it had in these 3 different nights. So, this seems really great. There's a catch though. I had to have known what the asteroid's velocity was. So if I'm trying to find this thing, I didn't know it existed before I looked at these images. If I didn't know it existed, how am I supposed to know its velocity? That seems like a problem. So if we can have a method that can actually just try this for every possible velocity an asteroid could have, then we'd be in business. That sounds ridiculous until you hear about these things. GPUs, graphics processing units. And so, they're developed for video games to decide, what each pixel on your screen should be displaying, when you're playing a video game. But really, these are computer hardware that's designed to do the same thing for a whole bunch of pixels really quickly. And with a GPU, you can actually test hundreds of possible velocities every minute. And that's fast enough to actually just test all possible velocities a Kuiper belt object could have in a reasonable amount of time. And so just to give you an overview of how this computer program works, let's zoom into an imaginary 4x4 pixel patch of those images where we're going to look for asteroids. And let's say we've got 3 nights again. And let's narrow the scope of our problem. We're only going to look for asteroids that are moving 1 pixel to the right every night. So let's just pick some random pixel to be our starting point. Let's try to test whether there's an asteroid that started in this pixel on night 1 and then continued on to the right. So I start with this pixel that I've chosen. And on night 2, if I assume the asteroid has moved 1 pixel to the right, I know that the asteroid is going to be in this other pixel on night 2. And so I'm going to look there, figure out that pixel's brightness, and add it to my running total. I want to see whether this adds up to enough brightness to give me an asteroid. And then I can do the same thing for night 3. By the time that night 3 rolls around, my asteroid has now moved 2 pixels to the right. And this is all fine for one starting position, but astronomical images are huge. You have to do this for every possible starting pixel. So even in this 4x4 pixel patch, I've got to have 8 possible different starting positions. But the nice thing about how GPUs work is that they're really a bunch of tiny computers called threads, all locked up together into one case. And what we're going to do is we're going to repeat this process for all 8 of these starting pixels. And we can have 8 threads on the GPU kind of independently assigned to each of these 8 pixels. One thing that the GPU really likes is when you use consecutive pixels out of an image. The fact that we're grabbing this 2x4 patch out of the image, like that's super efficient. That's going to be really fast. So each thread is going to pick a different pixel to start with on night 1. And then we're going to have each thread move over 1 pixel to the right. And so we're giving each thread exactly the same instruction, just different starting points. And again, this is really efficient and fast to do. And we can repeat this instruction for night 3. And now we have brightnesses for all 8 possible starting pixels over these 3 nights. And so just for visual's sake, I've shown you just a short 4x4 pixel patch, but GPUs can easily do this for 4,000 pixel by 4,000 pixel images. It's not even a problem. And so this procedure is actually fast enough that you can try all reasonable possible velocities. So this is the procedure of testing one velocity, 1 pixel to the right. It happens super quickly, so fast that you can just repeat this procedure for 2 pixels to the right, 1 pixel up, 1 pixel down plus 1 pixel left. You can just try all the possibilities and see what comes out. And so to show you what this looks like on real data, here's what this GPU accelerated shift and stack can do. So on the left is a grid of 20 images, all centered around the trajectory of a Kuiper belt object. And these 20 images were taken over 4 different nights. You probably wouldn't believe me if I told you that there's a Kuiper belt object in most of these images. Most of them just look like noise. There's a couple where, you know, maybe second row, second column, if you squint, that apparently has a signal to noise of 7. You can maybe sort of see something's there. But this set of images is not very convincing. And imagining having to look for this kind of blindly without computer assistance, you know, that would be impossible. And so if we think about this signal to noise ratio that tells us how easy it is to see this Kuiper belt object, in each individual image, this Kuiper belt object is too faint to see in just one image. But if we use shift and stack, and again, we've got a procedure that's fast enough that we don't need to know this asteroid's velocity beforehand. We can just guess all the possibilities and see what comes out. You can stack all of the images together and get something that's way more convincing with a signal to noise of over 16. And because it's on a trajectory that's consistent with a Kuiper belt object, that's pretty convincing that there is something there. And again, this is the sort of object that we can only recover with this computer assistance because it's not bright enough to see in each individual image. And so we can't just look for it moving in each individual image. We need this procedure that allows us to guess its velocity to see what comes out. So with my collaborators over at University of Washington, we started applying this to all sorts of data sets. And so here's one where we just, this procedure dug up 99 objects, of which 75 are not associated with known Kuiper Belt objects. So we have candidates for 75 new Kuiper Belt objects. And so a histogram of the brightness of each of those candidates is in orange down here. Again, bright on the left and faint on the right. And for comparison, we looked to some theoretical models that tell us how many asteroids we should have found in this patch of the sky. If everything was 100% efficient, we should have gotten the blue line. We have to knock that down to the green line for reasons like the CCD chips on the camera have gaps between them because real life engineering is hard. Okay, so that knocks us down to like 75% efficiency. But we're finding, it seems, most of the objects that are there. And we can draw a line on this graph that says, you know, everything to the right of this black dotted line is so faint that you wouldn't have been able to see it in an individual image. You would only be able to see this object by combining the brightness across multiple images. And you can see from this histogram, there's only a handful of these Kuiper Belt objects that are bright enough to see directly. And the vast majority of the objects we're finding are only findable using this method. And so this is super exciting. People over at University of Washington are super excited for when the Vera Rubin Observatory opens up and we can apply it to a huge data set. As we prepare for that, work that's in progress now is applying this method to data from the dark energy camera in the DECCAM Ecliptic Exploration Project. And so what I can share is this conference abstract where we found 109 trans-Neptunian objects, Kuiper Belt objects, of which 105 don't seem to be associated with known Kuiper Belt objects. And we're able to link them, we're able to find them across multiple observing sessions. And because we've spotted them over these long time baselines, we also have a good idea of the orbits of each of them. And so we can make sure that each orbit is consistent with what we think the Kuiper Belt is doing. And we can even start making measurements of these super faint Kuiper Belt objects, because knowing, you know, their semi-major axes or inclinations or eccentricities tells us about what must have been happening in the early solar system. And so digging up these Kuiper Belt objects with computer assistance, I think is going to be really exciting. And so, you know, getting after these faint objects that we can only dig up with computers and statistics is the sort of thing that I really like doing. So to wrap up my talk for tonight, I'll just go back to that flow chart I presented of the sorts of specializations in astronomy. And I think both because of the amount of data that astronomers are collecting, but also its complexity, right? Like now we've got crowded images. Now we want to find the faintest Kuiper Belt objects we can. You know, astronomy has this demand for trying to make the most out of our images. And fortunately for us, this has coincided well with the rise of computer technology. You know, now it's really easy to, well, relatively easy to get enough computer power to write algorithms that will really make the most of our data. And so at least during my time in academia so far, I think I've seen, you know, more and more people really get into learning about statistics and computer science. And I think this is becoming its own specialty, almost like hardware instrumentation. And it's important to remember, this is just one link in a chain. You know, whenever a new telescope comes out, JWST, it's awesome, right? A new instrument always allows us to see new things. But with software, sometimes a new computer program can even allow you to see new things. And so with that, I will end my talk and take any questions. Yeah, that's a great question. I'll just repeat the question for Zoom. So my opinions on AI in astronomy. First thing I'll say, I think AI has become definitely a buzzword. It's like the sort of thing that you can put into your grant proposals if you want people to give a second look at it. But that being said, I don't think it's completely hype. I guess I prefer the term machine learning, which I really see as just kind of another branch of statistics. And it gives you these really flexible models where, okay, you don't need to have a prescription going in of this is what my computer program is going to do. You can allow it to learn from the data. I'll put learn in quotes, kind of the best way forward. And at least in my opinion, I guess I'm wary of publications that are just like, we threw a bunch of data into this AI thing and here's what it spit out. I think the best uses of machine learning are where you use it in concert with your understanding of the physics of what you're looking at, or with your understanding of the statistical properties of the telescope or camera that you're using. And I think there's been a lot of exciting work there. And it's, yeah, machine learning or AI specifically, you can look at the papers that have been published. It's become a lot more popular in the last few years, I'd say.
Okay. Actually, they can't hear you online.
Oh, okay. Stephen, great talk. So I'm interested in this process, the algorithm itself. Quantum computers, would that help allow you to analyze even larger images if it ever happens?
Possibly. I haven't sat down to think about what quantum computers can do. I think it'll be a while before they'll be at the scale where we can use them, although I could be surprised. But there is a type of quantum computer that basically solves for the ground state of whatever energy landscape you give it. And I think there's actually a way to use that to just maximize likelihoods instantly, which is pretty crazy.
Okay.
I think it's a while before we can get computers that do that, but I'm sure they'll, open up all sorts of possibilities.
I actually got another question. That you showed an image where you had a rather small field, and then I think there were lots of images there, and then you showed where that 16:1 noise ratio, where, that one. Could you tell us where in those images the asteroid actually was?
In the very center of each of the smaller images.
Oh, okay. Like, because it kind of looked a little bit like it was enhanced at the middle.
Yeah, and it's there's even, and for reasons that I'd be happy to get into over the coffee break, there's even corrections that I think we did not make to the orbits. We assumed, okay, over the time period we're looking at, this asteroid is traveling in a straight line, and that would be at the center of each of these stamps. But of course, gravity is a thing. You've got some curvature, and that can actually give you offsets of a couple of pixels. And we have mechanisms of dealing with that now. Yes, these images have already been centered on the trajectory. Yeah, so these have already been shifted. Yeah.
Okay, I think we have time for one more question. Anyone?
I was just wondering what language tends to be used for programming all this stuff up.
Many. So for some reason, astronomers like Python. That's just, I'm not sure how that arose, but that's the state of the field. For my work, often especially for the GPU stuff, some critical parts of the program, you get a lot of benefit by writing it in C, in a lower level language, to really get a speed boost. My PhD advisor is raving about Julia and saying like, oh, it's a high level language, a low level language performance. I haven't been converted yet, but maybe he'll convert me in a bit. I know he and some of his current students are using Julia as well.
All right, probably sneak another one in. One more, anyone? Did you want? Cool.
Well, I was just thinking about some of the recent JWST images, which of course doesn't have atmospheric blurring, but is crowding, like some of the gravitationally lens galaxies, like you see like just tons of galaxies all over the place. Can this kind of algorithm help out there, even though they aren't point sources?
So that's a very good question. And the statistics is a lot easier for point sources. But in principle, as long as you can model it, if you can model what your galaxy should look like, you can just throw it into the statistics. And this is actually one of the applications of machine learning that I think is really exciting. There's some work by other groups of basically using machine learning to come up with a neural network that can generate every sort of galaxy that's out there, every sort of galaxy shape, and just give you this nice parameter space that you can just fit. And it sounds wild, but I've looked into it, and I think that sort of thing is actually the way forward to deal with galaxies, because they're not just, you can't just throw up an ellipse on your image and expect that to work. Galaxies are way more complicated.
Okay, well, thank you very much, Stephen. That was a great start off. That was pretty entertaining, and thank you very much. And again, thank you everyone for give Stephen a hand for that presentation. Thank you. Okay, just we have one announcement coming up. Jeff, you want to come on up? And Jeff has an announcement while I figure out our screen sharing.
Thanks. Okay, it's May, but September isn't that far away. And I'm here looking for volunteers for the Beaver Hills Dark Sky Festival, Milky Way Day on September the 3rd. We haven't done it for 3 years, so Astronomy Day went really well after a three-year break. So we're going to be out at Elk Island at Stoughton Lake on that's Sunday. I was out at Elk Island talking to the people there last week, and they're really excited about this. So I have my sign-up sheet here. If you can volunteer, I'll also have it back next month too. So leave your name, phone number, email. If you can bring a scope or a solar scope, or if you want to work at the information booth or help with setup or takedown, or just be a floater, or the ubiquitous other. I'll leave it here on the stage here if you want to come and sign up. That would be really appreciated. So thank you very much. Oh, and I really like that video at the beginning. It reminded me of my youngest when they did a high school performance of Grease, and brought back some memories.
What's the date, Jeff?
September 3rd. It's a Sunday.
Okay. Usually a pretty fun event. Okay, I think we'll take a bit of a break, and I have since I can't find the time there, I have 8:32. So how about we'll reconvene at 8:45. Okay. It's 8:45 plus 2. So if everyone can start taking their seats again, we'll get second half of the meeting underway.
So tonight, I presented here before, as you all know, but tonight I'm going to present a star tune pulsar, which I've actually already presented way back in November 2021. It's the first one I did. And at that time, I didn't have an introduction, but I've put in an introduction. And the reason I'm presenting it, because it's the presentation that's farthest removed from what I've presented in the past. So I'm hoping that most of you won't remember it. You're gonna go think it's new. The reason I'm doing that is because on, I guess it was Saturday, I was working on the one I was supposed to present. I said, this is not going to work just yet. I need another little bit to work on it. So I dug through my archive and said, I'll do the pulsar one again. Oh, yes. So a pulsar is a neutron star that produces very rapid and regular pulsations in light and radio waves. It's most easily detected in the radio part of the spectrum. And it's a combination of the neutron star's rapid rotation, its strong off-axis magnetic field, and the presence of a diffuse plasma, which is delivered through tidal interactions by a close companion. I picked that off the internet. I didn't make that up myself. I didn't set out to write a song about pulsars. It just kind of happened one day. I picked up my guitar and I started picking, it's sort of a regular pulsating beat emerged. And can I find the arrow button? Here it is. There it is. Yeah, and I said, hey, it sort of sounds like a pulsar, doesn't it? And then I Googled pulsar sounds and listened to a few radio pulses. So this short video was, it's an extract from a YouTube link that sounds, the sound directed corresponds to radio waves emitted by the brightest pulsars in the sky. So you can hear my guitar picking didn't sound much like a pulsar. Oops, sorry. There it is. Not quite. Regardless, I set out to write a song about pulsars. My background in astrophysics provided enough information to generate a few meaningful lines of poetry, which morphed into a conflict of sorts between two lovers. In the song, the neutron star and the companion, like two conflicted lovers, are endlessly arguing and metaphorically dancing in the night. But first, I'd like to give you a little bit of background at pulsars. So this is something I just grabbed off of the internet in the last minute, so I didn't have to generate the information myself, but here we go. It should now play by itself.
A pulsar is a rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star. A teaspoon of matter from a neutron star weighs as much as Mount Everest, and a neutron star is so compact that a ball about 15 miles across contains more matter than our sun. Neutron stars spin between 7 and 40,000 times a minute and form with incredibly strong magnetic fields. Rapid spin and intense magnetic fields drive powerful beams of electromagnetic radiation, including gamma rays. As the pulsar rotates, these beams sweep the sky like a lighthouse. To To a distant observer, the pulsar appears to blink on and off. Pulsars slow down as they age, but some of the oldest pulsars spin hundreds of times a second. Each of these millisecond pulsars orbits a normal star. Over time, the impact of gas pulled from the normal star has spun the pulsar up to incredible speeds. This accretion may be the cause of their weaker magnetic fields. Despite this, these pulsars also emit gamma rays.
I think about it every time when I look at the moon. I wonder if you think about it, if there is any room. I wonder why we're here, concerned that you do not, saddened by the fact I know, regretting it a lot. When I gaze up at the night, I look into your eyes. Deep inside I feel torn, we don't seem to agree in which direction we should point, like a lighthouse on the sea. We're in some kind of universe, an everlasting bond that even lovers dream about. If it was up to me, I would cry forever, send my tears into the universe. I hear you calling endlessly, your message stays the same, the rapid beating of your heart like a magnetized machine. Long ago it was said that it would end this way. The law of gravity will apply until our dying day. If it was up to me, I would cry forever, send my tears into the universe. When I gaze up at the night, I look into your eyes. I think about you every time when I look at the moon. I wonder if you think about me, if there is any room. We're in some kind of universe, an everlasting bond that even lovers dream about. When I gaze up at the night, I look into your eyes. We are dancing in the night, it's been going on forever. Dancing to our own delight, it wasn't meant for you. We are dancing in the night. We are
Thank you, Orla. Educational and entertaining. Okay. So our next item on the agenda, just shook things up a little bit, moved Astro Imaging Corner up a little bit. So next item is over to Abdur for Astro Imaging Corner.
Perfect. Thank you, Jay. Okay, so I'm going to share my screen. Let's hope this works.
Okay, good to go, Abdur.
Awesome. Okay, can everyone see my screen? Astro Imaging Corner. So let's get started. Welcome to Astro Imaging Corner number 129. Okay, sounds good. So for anyone joining us for the first time, this is the part of the meeting where I share images that were sent in by the members. And if you want to send in your image, just send it to Astro Imaging Corner at edmontonrasc.com. And you can find that email address at the bottom left corner of the RASC Edmonton webpage. So we've received quite a few images today, mostly because some of our members were down south in Australia and they sent in a lot of images. So I'm going to go through fairly quickly. But first, I'd like to issue a correction to last time's Astro Imaging Corner. I had credited this particular image to Craig Sherris, but he reached out to me as well to let me know that it was actually an image from Alan Hobbs. I think I must have been exceptionally sleep deprived that time to have missed that. So just want to correct that this particular awesome image of Thor's helmet was sent in by Alan Hobbs last time. And again, this is an emission nebula in Canis Major, and this was captured using Nina and a C8 Edge HD and Alan's ASI 2600 MC camera. And this time, Alan had sent in an image of the Eagle Nebula. Now, this is an open cluster in the constellation of Serpens covered by this nebulosity, and it consists of several star-forming gas and dust regions, including the pillars of creation that were popularized by the Hubble Space Telescope image a long time ago. And this one was taken in New Mexico near Silver City by Alan on March 27, 2023, using the same equipment as the other one. So beautiful shot there, Alan. Up next is an image of the eclipse from Australia, from Arnold. And these are actually, this one and the following couple of images are actually just single subs that Arnold had processed on his phone. So they haven't been stacked or really processed yet. So I look forward to seeing the other images. And this is an image of what we call Bailey's beads at C2 with the prominences visible around the sun. And this was taken with a Canon 6D and a 70 to 200 millimeter lens and a 2x tele extender. And this was from Exmouth, Western Australia. So beautiful shot there. And this is at mid-eclipse, so near totality, and you can see a beautiful view of the outer atmosphere of the sun. Up next is an image of the Large Magellanic Cloud from Arnold, and this is also known as NGC 2070 or 30 Doradus, or the Tarantula Nebula is visible near the right part of the LMC. And again, this was also taken with the Canon 6D, I believe. Up next is an image of the Small Magellanic Cloud from Arnold. And at the bottom left, you can see 47 Toucan, which is also known as NGC 104 and is a very nice and bright globular cluster. Up next, another image from Arnold, and this is the full extent of the Milky Way captured with a Canon 16 to 35 millimeter lens at 16 millimeters. So you can see the entirety of the Milky Way, including the bright core there. So great job, Arnold, and thank you for sharing. And last image from Arnold is one of my favorite objects, the Eta Carina Nebula. And this was captured using a 70 to 200 millimeter lens at 200 millimeters. And this is a 30-second exposure at ISO 1600. And again, this was also taken from Australia on April 28, as it's quite too low for us to image or see from our latitude. Up next, we have an image from Warren Finlay, and Warren says that he finally managed to finish observing the last of the Herschel 2500 objects on the night of April 16, 2023. And well, it only took 22 years for Warren to accomplish this. And Warren has attached a celebratory self-portrait taken just after he completed the last object on his list. And this photo is a single capture of 30 seconds just using the ambient light at f1.8. And Warren says that he's a little bit blurry because it's tough to stay perfectly still for 30 seconds. And a lot of the air glow can be seen near the horizon. And Warren wants to clarify that the glass contains iced tea, not wine, as unfortunately booze and stumbling around in the dark don't go together so well. So congratulations on this accomplishment, Warren. That is a lot of objects. Up next, we have an image, a first image submitted by Zeidler, and this is the aurora from his house. This was taken on a Samsung Note 20 Ultra from Edmonton and edited in Lightroom, and this is from May 5, 2023. So this really shows us how amazing smartphones are these days and what they can do. It would have been unbelievable even just 10 years from now. So great job there. And just by coincidence, one of our other members was actually imaging the aurora at the same time as well, from what appears to be a very similar location. So this is from Josephine Christensen, and this image was taken with the Samsung Galaxy S22 handheld using night mode, and this was taken from the Windermere area in southwest Edmonton. So yeah, very, very nice shot. Thank you for sharing. And also this other shot from Josephine was also taken with the same equipment. And it looks like it was quite the show. Beautiful. And lastly, another shot from Josephine, also from her house in the Windermere area. And up next, we have an image from Brian Martin, and this is M106. This is another one of the gems in Canis Venetici, and this is a total of 14 hours of exposures in LRGB using an RC10 and a focal reducer for a focal length of 1360 millimeters. And the camera used was Brian's old QSI 516. And Brian says that the sky at his home observatories is now approaching Bortle 6, so it's becoming increasingly difficult to pull out faint detail in most DSOs. I completely understand, Brian. I'm in a solid Bortle 6 or 6.5 or so right now myself, so I know exactly what you mean. But despite that, you've been doing some amazing work, so I hope to keep seeing more of your images. And this is another one from Brian. This is Messier 45 and the California Nebula at the very left of the screen there. And this was taken at Arches National Park in Utah from Brian's September road trip there. And this was with a Canon 6D and a 35mm Samyang lens. And again, this was from a stock camera. It was not astro modded, so it's quite amazing what you can capture with an unmodded camera from a dark location. And up next, this beautiful image of the Milky Way area was taken by Brian in Dorothy, Alberta in April. And the thin clouds obscured the Milky Way, but sometimes clouds can add interest to a shot. And this is a preliminary image for a spring-summer project of starscapes in southern Alberta. And yeah, I look forward to seeing more from this project. And this one was taken with a Canon 6D and a 24mm Rokinon lens. Up next is an image from Ray. This is the whale and hockey stick galaxies, one of my favorite combinations. And this was with a QHY268C and a William Optics 132mm telescope. So great job there. Next from Ray is this beautiful shot of the aurora. This was taken from Edmonton from Ray's backyard. And this is a 1 second exposure at ISO 640 with a 24mm lens at f1.4. And Ray says the aurora lasted about half an hour over a 3-hour period he was outside. And this was actually shot during the full moon, so that shows just how bright it was at the time. This is Messier 101, shot using an Optolong L Extreme filter and the same 132mm triplet APO, and it was processed in Lightroom. So because of the L Extreme filter, you can see some good detail there in those hydrogen alpha regions in this galaxy. Up next is one of the recent images from Murray Paulson's trip to Australia. And Murray says that the eclipse was spectacular. It was short, but with the advantage of exposing so much of the chromosphere. The eclipse lasted 56 to 57 seconds based on his measurements, and it was predicted to be about 57 seconds. And Murray said that they were in Exmouth, Australia at the time, and the sky was absolutely clear. And he had a 71mm William optics scope on an equatorial mount tracking the sun for the duration of the eclipse. And the camera was a Canon 80D, which he had operated using an Arduino that controlled the shutter for the eclipse. And the camera did some auto bracketing, and these photos are only saturation enhanced with no other processing. And in this image, if you zoom in on it, you can see at the 1 o'clock position, there is a prominence right over here that's floating about 220,000 kilometers from the sun. So a very nice shot. And this is from totality, where you can see a huge amount of the solar atmosphere. And this one over here, you can see the full extent of the atmosphere there. So again, beautiful shots. And this is, I put together all of Murray's shots because I couldn't show all of them. So this is from beginning to the end of the eclipse, showing you the full progression. So I'll be taking notes for when I visit Texas in 2024 to try to image the eclipse down there. And lastly, this image from Murray shows some of the globular clusters at the same scale. So these are Messier 13 on the very left, which is one of our best globular clusters. And then there's M22, which is my favorite out of all the globulars that I have seen, but it's quite low on the horizon for us. And then at the very right is Omega Centauri. So you can see just how much bigger and brighter Omega Centauri is than all the other globular clusters. So I would love to see Omega Centauri someday, especially after seeing these pictures from the south. And these were all taken using a William Optics GT71 and a Canon 80D. Up next is an image from Craig, and I put globulars for some reason, but this is the Pinwheel Galaxy M101. And this was taken on April 12, 13, and 16, 2023. And this was a total of 10 hours of exposures using a Skywatcher Equinox 120 ED and Craig's software BISC Paramount MX mount and a IMX 571 camera. So beautiful shot and very nice processing, Craig. Up next is an image from Dave Mussel. This is Thor's helmet. And Thor's helmet is a supernova remnant lit from within by an intense Wolf-Rayet star that's located in its center. And this object is located in the direction of Canis Major, about 15,000 light years from Earth. And it's visible at our current latitude in the winter low in the south. And Dave says the Wolf-Rayet stars are often found in the center of planetary nebulae, and as a group are generally far hotter than the average stars in the Milky Way galaxy, and they are between 20,000 and 200,000 Kelvin. Despite their intensity, they're not always visually bright because so much of their output is in the form of UV radiation. And it's this radiation that's responsible for some of the brightness of the nebular regions around them, as seen here in Thor's helmet. And another factor in the structure and brightness of the nebulae around Wolf-Rayet stars is the stellar winds which they typically generate, which when they collide with slower moving interstellar gases, heats up those gases to incandescence, which is marked by the luminous shock waves. And the data for this image was collected on a trip to New Mexico in March. And it integrates over 4 hours of data captured through narrowband HA, S2, and O3 filters. And the telescope used was a 5-inch APO on a Skywatcher AZ-EQ6 mount. So beautiful shot there, Dave. Up next is an image from Mark, and this is an image of the smoky Edmonton sunset. And here's a wider view of that. So especially with all of the wildfires going on in Alberta, the sunset might look like that for the next little while. So thank you for sharing, Mark. And up next is one of my images. I haven't gotten the time to do any imaging or processing for the last little while, so I think this was taken a couple of months ago, and it was one of my last images with the ASI 1600 before I sold it. And this is actually a really interesting galaxy. I was looking at it visually as well not that long ago, and it's a fairly bright galaxy at magnitude 10, and it's actually more luminous and larger than the Andromeda galaxy, and it's one of the brightest members of the Coma 1 group of galaxies, and it has a population of roughly 240 globular clusters, which is more than the Milky Way as well. And this was taken with my C11 at f2 and the ASI 1600, and this was a total of about 20 hours of exposures. And at the bottom right of the galaxy there, you can see some ancient galaxy clusters way far in the background. And I'd estimate probably between 1 and 2 billion light years away in the background. And here's a more zoomed in view of that galaxy showing the distortions in the disk of it. And these distortions in the disk are caused by some of the galaxies that are orbiting this one. And I know it has at least 2 different galactic companions, and probably a few smaller ones that it collided with at some point in the past. And this was a recent project I did where I tried to make a little time lapse. And at the top right, you'll see a sunspot group there where there is some motion going on. So keep an eye on the top right there. So right here, you can see the plasma falling back to the solar surface, and that creates these intense heat spots on the solar surface. So those are called Ellersman bombs. So I'll try to do a longer panorama or a longer time lapse at some point one of these days when I get some time, but this was probably over about 1 hour or less. Oh, and there we go. And my last image is of an object that I've been trying to get a decent image of for a while. I haven't quite succeeded yet, but a couple of us recently took a look at this object when I visited Edmonton for the Astronomy Day party at TWOS. And Luca and I were looking at this cluster, at this crater. This is called Hasadus A. And it's a very interesting ringed crater. So there's this brighter outer crater, and then inside there's another perfectly concentric ring. So I'm not exactly sure how this crater formed, if it was an asteroid that broke up and both of those parts impacted, or it's just a coincidence that a second impact happened exactly in the dead center of this primary impact. But it is an interesting crater to try to look at visually. And I've seen this structure with everything from a 4-inch refractor to my my 16-inch Dob. So this image was taken with a 4-inch 100mm f9 Skywatcher refractor and my QHY 462 guide camera. So that is it for tonight. So a huge thank you to everyone who sent in some images, and I hope to see more next time as well. So thank you, and clear skies. Back to you, Jay.
Fantastic. Thank you, Abir. Great pictures as usual, everyone. Please keep them coming. Okay, as we will run into the end of the meeting here. Oh, look at that. Like I said, last bit of the meeting here, we'll do a quick book of the month. I think hopefully Mark is here. Is Mark here? No.
Does it really matter? Good evening. Greetings from Berta Beltran and I, co-librarians at the Lucian Kimmel Library, which is located just off the main entrance to the Star Theater. We have 2 books of the month tonight, one from April and one for this month. April's book is The Last Stargazers, recommended by Arnold Rivera. Actually, both books were recommended. The New Horizons book was recommended by Robert Garapi. And if you see a book you'd like, we can purchase it, and you have first dibs at reading it, and then we have it for the rest of the membership. to have a look at in the future. So the April book of the month is The Last Stargazers, recommended by Arnold Rivera. It was published in 2020, and author Emily Levesque shares some of her experiences as an astronomer working at one of the largest observatories in the world. She also shares tales from other observatories, for example, the McDonald Observatory in Texas, where in 1970 a shooting occurred. Yes, a former employee shot the telescope. The man was arrested and the telescope kept on working. As for the May book, yeah, The Pluto System After New Horizons, recommended by Robert Garapi. Noted Pluto researcher Alan Stern is one of the editors of this comprehensive volume that contains 25 research papers resulting from the findings of the New Horizon probe in 2015. Topics covered in the papers range from the colors and photometric properties of both Pluto and its moon Charon, the surface composition of both bodies, the dynamics of Pluto's atmosphere, and the New Horizons exploration of the primordial Kuiper Belt object Arrokoth, which looks like a snowman tumbling through space, sans eyes and carrot. So yeah, 25 interesting papers in this this new volume. So both books are available tonight for borrowing. So thank you very much.
Astronomical trivia. As the sun traverses the ecliptic path, it appears to move against the band of 12 ancient constellations of the zodiac. So the trivia question for tonight is, what zodiacal constellation does the summer solstice occur? Feel free to just shout it out or type really loud on Zoom. Anyone? I hear Gemini. Taurus, I hear Gemini, I hear Taurus. Okay, the answer is indeed Gemini is the constellation for the summer solstice, but not without a wrench. But wait, is it really Gemini? Because as a result of precession, around 1990, the summer solstice crossed the modern boundary from Gemini to Taurus, which now technically holds the point. But because summer solstice is closer to the classic figure of Gemini than it is to that of Taurus, and since Gemini, of course, along with Pisces, Libra, and Sagittarius, quarter the ecliptic, Gemini is still traditionally taken as the solstice celestial home. So there you go. Hope you learned something from that. And thanks to Jim Kaler, who's a professor emeritus from University of Illinois for that content. And that was Russell Sampson for submitting that idea. Okay, final item, few announcements. So I'll just go through this quick. Again, I just want to address that unfortunate circumstance that I think almost all members across the nation, actually, of the RSC received an email from a former fund development contractor that was brought on by the RSC National. And in that email, she had alleged quite a few bad actions by the RASC National Board. And so your Edmonton Council just thought it was important that we address this, that while we do not agree with her methods of communicating that by using the entire national email lists for that information or for communicating out her allegations, nonetheless, some of the allegations that she had stated in her email were pretty serious. And so your Edmonton Council has asked our national reps, Sukrit and John, to make sure that National addresses those. So we don't want them to go unanswered. Some of them may be unsubstantiated altogether, but we still would like to hear some answers from National as far as those allegations go. So they'll be looking into that. If anyone has any greater concerns or comments on that situation, by all means, please feel free to reach out to me, send me an email. Good news side, storage locker. So we managed to get into our storage locker after the fire. And it was really quite anticlimactic, actually. We opened that door with bated breath and everything was just normal. So it was just exactly as we left it. So nothing, no damage, anything like that. And so we moved everything out of our old locker, affordable storage, into a new one on the west side. So thanks again to Jeff, Kathy, and Luca Vanzella, Alistair and his daughter Elizabeth, Clayton and Sharon and Daisy for all helping with that move. So all the equipment is in good order. And just finally, International Astronomy Day. So it was pretty good. It was felt like old times. So we had beautiful weather out there. We had about 20 RASC members throughout the day show up, various solar and evening scopes. Probably between, I would say, 350, 400 members of the general public showed up throughout the day. So that was really quite fun. So it's the first time in 3 years for me to do that. So that was thrilling to do. And so thanks to everybody that did show up and help put the RASC's best foot forward there. And thanks to Frank too, by the way, for opening up the observatory as well. So lots of options for people to observe. Just a quick note there that one of our members, Doug, not sure where he went over there. So he just had a Celestron power tank there that his charging cables went missing. So if anybody was there and happened to pick them up, could you please maybe just send me a note and I'll get a hold of Doug. Get him his charging cables back. So upcoming events. Next What's Up over Edmonton. Again, Jeff Robertson and his What's Up. Wednesday, May 31st at 7:30. Really, everybody should attend that. So it's very informative, gives you a quick update on what's coming up in the next month. So it's pretty interesting and Jeff always makes it super entertaining. So if you haven't attended it yet, you should make an effort to show up. Observers group, John Stolte and Berta Beltran as well, May 10th, 7:30. Astro Imaging Cafe, Richard Covey. And is Richard online? I know Richard wanted to say something quick. Can we activate his mic, Frank, if he's there? Okay. No, Richard. Okay. Well, Richard, it does have another Astro Imaging Cafe on May 17th at 7:30. So look out for more information on that on our website. And our next monthly meeting is Monday, June 12th at 7:30. So with that, I bid everyone adieu. Thank you for your attendance. Thanks to those that participated in the presentations, and everyone have a good night. I call the meeting adjourned.
Good night.